quantify how much shielding we get is by a divider. So the dielectric constant is the divider of how much is the net field cut. Oh, whoops, that should be the external. How much is the net field cut from the external? Okay. So that just turns out to be a more convenient way to describe how it's cut. So for instance, if kappa is 5, that was the example I think I gave last time, then we get so much partial shielding that the net electric field is 1/5 of what it would be without it. Okay? So 20%. So the net field is 20% of what it would be if the dielectric weren't there. And of course, if you only have 20% left, it means that the induced field must have taken off 80% of what was there. So you have external field, you take off 80% of it, what do you have left? You have left 20%. And if you solve this symbolically, of course, if this is 1 over kappa, 1 minus 1 over kappa is what you took away, okay? So that's the partial shielding aspect. And as we learned last time, it's not that we like the partial shielding, but partial shielding gives us an opportunity to do something we wouldn't not have had the chance to do otherwise. So if we stick in a dielectric and it shields off some of the field and it reduces the voltage also, then we have the opportunity to put more charge on there than we ever could have gotten on there because of the suppressive effects. So we get more charge on there than we ever could have. So we increase the capacitance by kappa. Anytime you have the dielectric material in between the plates, you've increased the capacitance by kappa, and you're able to store more charge and more energy at the same charging voltage. Okay? So if you have a battery charging this thing up, it's the same 9-volt battery or whatever, but you're able to get on way more charge and way more energy, potentially, than you could have before. And the reason, again, for that is because the dielectric suppresses the voltage, so you need that much more charge, which stores that much more energy, onto the plates before you can climb up to that voltage, the charging voltage. So, that's kind of where we were at, and some of this background I'm going to need when I now start looking at how do I design the best capacitor possible for my application. So if you're in an engineering situation, you need to select a capacitor, what would you do? Okay, so let's take our capacitance formula, looks like this. And let me go ahead and put in, for an instance, for a parallel plate capacitor, we learned that the physical construction determines the capacitance. So here's what we have. So we have 2 plates, each of area A. Don't forget that is the area of each plate, not the combined area. They are separated by D. And now, as part of the physical construction, we have inserted in between the plates a material with dielectric value kappa. Okay. First of all, just in case you ever encounter this, sometimes these two are grouped together. So if you ever see this, I'm not going to use it. This thing is called, again, just to remind you, the permissivity of free space. I haven't told you why it's called that. I've just kind of characterized it as a shuffling around of Coulomb's constant. But sometimes the kappa of the material times this is itself called just epsilon without the naught. This is called the permissivity of the material. So combines the properties of nothing with the properties of the particular dielectric you're using. We call it the permissivity of the material. I'm not going to use that for the main reason that it's not like it's a big deal to write two variables. And this thing is really easy to confuse with battery EMF, even though it has nothing to do with that. Okay, so that's not battery EMF. So I just wanted to introduce that in case you ever see it. For instance, if you ever look up the formula for a capacitor with a dielectric and you go, where's the kappa? The kappa may be absorbed into another variable. Okay. So what I want to take a look at is I have really three main ingredients. I have A, D, and kappa. These are all things that I can consider when I am constructing a capacitor. And let's say that our goal is to make the largest capacitance value possible. Okay, so let's make the best capacitor possible. Okay, we want the, I guess I should say, the highest capacitance that we can. So let's take a look at what we can do with each of these variables. Now, first of all, hopefully it's not a stretch to understand why we might want to create a high capacitance value. That improves the storage capability of our device, right? That means we can store more charge at a given voltage. That's what more capacitance means. It's much akin to making the best battery that you can. Okay, so we talk about making batteries. You're working for Duracell or something like that. So you want to make the longest lasting 9-volt battery you can, right? Which means that you can store as much charge on that as you can for the fact that it still needs to operate at 9 volts. Now you can store more charge on something, but usually more charge comes with more voltage. So if something has more voltage, or sorry, it stores more charge, you don't want it to be necessarily more voltage. So for instance, if you have a bunch of charge, we learned that a bunch of charge creates a bunch of voltage. So no one wants to hear, I have this really long-lasting battery, but sorry, it's not 9 volts, it's 1,000,000 volts. If you plug it into something, it will fry it. So the whole point of a dielectric is that it allows you to get more charge for the same charging voltage. Okay? So when we're talking about making our capacitor, think about why it is that we want to create a high capacitance. Now there is a difference between a battery, which runs an internal chemical reaction, and these simple capacitors we're talking about, but the same considerations are there. We want as much charge as possible stored, but we don't want to have the high voltage that comes along with it. So that's where the suppression effects of the dielectric come in. So let's talk about what we can do to make the capacitance as large as possible. The first and most obvious thing, I think, is to make the plates bigger. So we increase this area. So if we make both of our plates larger, it will make a better storage device. It's just like if you want to make the closet better, you can knock out a wall and make it larger. But there is a downside to increasing the area. What's the downside to making a big area?
Size.
Size. You have a size issue, okay? So there's always a catch. So the catch, in this case, is size. Nonetheless, you can play some cool tricks with this. You can create a very large area that takes up very little volume, right? The way you do that is you get really creative with how you pack that area in. If we're talking about parallel plate capacitors, of course, making them bigger is going to, bigger area is also going to make them stretch out further to the sides. But you have these capacitors where they do this. where you take a huge amount of area and you compress it into a tiny volume. Okay? So these are called electrolytic capacitors, and if you are having in your hand a capacitor that's something on the order of a farad or something like that, it is no doubt one of these. Okay? So there's some special capacitors where they can have a huge plate area, but not taking up a lot of volume. Okay? So these are not the kind of capacitors we'll look at. Obviously the calculation is more complicated there. So for us, making the plate's area larger will also necessarily cause it to have more size, and that may be a catch or a drawback. Okay, so let's take a look at kappa. What do we want to do to kappa if we're going to make the highest capacitance possible? Increase it, that's right. So we want to find a material which has a large dielectric constant. A large dielectric constant will be a very good partial shielder. Okay? So what would that mean? If we can find something that is kappa of 5, well, that's capable of reducing the net electric field to 20% of its value, which means we knocked off 80%. Which means, then, that if this is going to knock down the net field to 20% and knock down the voltage to 20%, remember they go together, I should put that here. Remember, E net and the voltage are directly proportional if you don't mess with the distance. So if you shield off the net field, you'll shield off the voltage. And if you have a charging battery, it says, well, no, you can't be lower voltage. It's going to instead pump on kappa times the charge. So in this case, you have to go to 5 times the charge to get up to the same voltage. Okay? So that's a good thing. But you're only going to be able to have the materials, or you're only going to be able to have access to certain materials. You can't just necessarily go rummage around in nature and find a kappa value that is huge. Okay, so you're limited by your materials. Materials available. And as you can probably guess at this point, they were not satisfied to use materials that you can dig around and find. They can manufacture and synthesize materials specifically to have a large kappa value that are extremely good partial shielders. In fact, they have kappa values in excess of like 10,000. So it cuts the external electric field by a huge margin. And in order to get back up to the original voltage of the charging battery, you have to put many, many, many times the amount of charge that you otherwise could have gotten onto those plates. So, let's look at the last one. What should I do to the plate separation to improve my capacitance?
Minimize it.
Make it smaller. Now this one seems like a win-win proposition. You mean I get to make the capacitor smaller and make it better? You get to put the plates closer together and it's better. Usually when you want to make something better, there's a catch, but this seems like a win-win proposition. Well, I'm here to tell you there is a catch. There is a catch called dielectric breakdown.
Sounds sexy.
So there's always a catch. And so your job as engineers is always to figure out what is the best balance of these factors for the particular application that you're looking at. Okay? So let's talk about what is dielectric breakdown. Okay? So, in order to imagine this, let's hypothetically imagine that we had a capacitor where we could have a dielectric in between, but we can make the plates closer and closer together, so we have to like be squeezing out some of the dielectric as we went. And we find out, let's find out what's so bad about that. Okay, so we have a capacitor that's being charged. This battery already has a dielectric. And we're going to imagine that we can bring these plates closer together and decrease the separation and find out what is so wrong with that. What's really going to happen here that is so catastrophic? Well, what's going to happen is this. If we have a certain amount of charge that we were initially able to get on here, when we bring the plates closer together and we improve the capacitance, more charge is going to be going on there. So the battery is going to backfill more charge. So as we decrease D, C is going to increase, which means we get more charge. So we're going to build up more and more charge. So more charge is going to get put on here. Not decreases, it increases, right? So it shields off more, right? So what we have is that E induced has to grow as well. So E induced has a larger job to do. Question?
How are we able to decrease D but not change now?
Oh, yes. Yeah, sorry. Let me back it up. I said something in error. So the battery holds this the same. And yes, I was wondering, I was saying this sounds wrong. So this increases, decreases, right? So this increases, okay? So the net field increases, and yes, so this increases, this increases. This is correct, as we will see. The reason why is that E induced has to cancel off a certain percentage, right, or fraction of the external. And so what happens here is that now, if the job of this is to cancel off a fixed percentage, there we go, it's not a fixed value, it's a fixed percentage of the external, then that has to grow as well, right? So here's my analogy, right? If you had to choose, would you rather have 80% of $1,000 or 80% of $1 million? Those are different amounts of money, right? They're both 80% of something, but 80% of $1 million is more money, yes? Okay? So this is rated as a fraction or percentage if you want, but just because you're canceling off a fixed percentage doesn't mean it's fixed overall, right? So what we have is that E induced has a larger job to do if E external is larger. It's still canceling off a certain percentage, but the thing that it's canceling itself is larger, or it has to cancel a fixed percentage of is larger. Does that make sense? Yeah?
So the 80% stays the same?
Right, that's the definition of a dielectric constant. It's a fraction or a percentage of how much does the external get canceled. But if the external grows, then canceling off a fixed percentage of it is going to require a larger amount overall, right? Does that make sense?
And
So, as you increase the charge on the plates, if the dielectric is going to cancel off a certain percentage of that, it's going to actually have to be larger itself, okay? E induced has to go from 80% of a smaller field to 80% of canceling a larger field, E induced has to get larger. So here we have to be careful, what exactly are we doing when we increase E induced? It's still a fixed percentage of E external, but it's a fixed percentage of a larger number. Well, we have to back up a step and ask how exactly is this created? How exactly does E induced get made? Well, if we take a normal atom from this material, so let me blow this up, something like this. A normal atom is like a positively charged nuclei with all the electrons more or less symmetrical around it, okay? This is a non-polar molecule, okay? So something like that, where essentially the center of mass and the negative charge and positive charge are all right on top of each other, then that alone won't make anything. So if E external is 0, then this, the induced field, is nothing. We're not doing any charge polarization if we haven't yet applied anything. But now, let's increase the E external and see what happens. So let's say E external is something like that. So we take a look at an individual molecule, and what's going to have happen is something more like this. It's going to have the minus, the electrons pulled upstream, of course, and the plus downstream. So now this is what's called an induced dipole, if you've heard of that from chemistry. We have sort of separated out the minus and the plus. They're not coincident in exactly the same place. And a bunch of these, one of these already is going to create an E induced. Of course, it points from plus to minus. And that's going to create a little bit of partial shielding. Of course, it's the sum total of all such atoms or molecules that creates our E induced in the first place. It's just the combined effect of a bunch of things like that. Well, let's find out what happens when we apply an even larger E external. Well, if you're going to cancel off a fixed percentage of that, you're going to have to increase the E induced as well, right? So for instance, if you need to cancel off 80% of E external and E external itself is increased, then this is going to have to increase. So what happens is the minus and plus of a given molecule gets stretched further apart to create a larger E induced, because 80% of $1 million is more than 80% of $1,000, okay? But here's the problem. I'm going to symbolically draw these guys like this. And I purposely kind of drew a little narrow waist there, because what's going to happen at some point?
They're not going to affect each other anymore.
What's that?
They'll be too weak to affect each other anymore. The charges, they're going to be too
well,
separate.
these guys don't need to affect each other. They just create an E induced. But what's going to happen?
Electric field's going to be weak in the middle.
Anybody else? Anyone else?
Electron's gonna fly off.
That's right. At some point, you're going to pull the electron off. You're going to snap this thing. At some point, the external field is going to get so large that the minuses and pluses in this atom are more bothered about doing what the external wants than being attracted to each other. So this is going to fly off this way and actually go upstream, and this is going to fly downstream. You've literally snapped the dielectric apart. And the electrons, which used to be bound to a particular nuclei, are no longer not. And if you suddenly have free electrons flowing around inside here, you've created, from an insulator, a conductor. And then you have a bad situation because you have minus charges flying up here and plus charges flying down here, and you're going to get charge cancellation. Remember, the whole idea of a dielectric was that you could create this induced field, but the charge was bound, right? You had these charges that were bound, they were next to, but didn't actually flow onto the plates. But now, since you snap the atom apart, they will flow onto the plates, and they will cancel the charge that is on it. So this is a bad thing, okay? This is called dielectric breakdown. And essentially the reason why it occurs is because if E induced is always going to cancel off a fixed percentage of the external, at some point, keeping up with that job of a fixed percentage, well, that's a larger job to do as you increase the absolute amount of external field. And so at some point, the atoms or molecules in the dielectric will not be capable of canceling off that percentage without breaking themselves. Okay? An example, a prime example of this is lightning. Lightning is dielectric breakdown. Okay? What do you have? You have a powerful electric field created between the cloud and the ground. And that field, it's very similar, basically, to a parallel plate capacitor. You have a powerful external electric field, and that electric field is so strong that the air molecules between, let's draw an air molecule between, it's so strong that will pull the electrons up and the positives down. It'll scissor that in half and will make the air conducting. That's what lightning is. It's dielectric breakdown between the cloud and the ground. So the question then is, how do we quantify this? Well, it's very simple. For dielectrics, we need two numbers to rate them. First is the dielectric constant.
Kappa.
The dielectric constant tells us about by what factor will the capacitance increase. But with every dielectric, there's a second number. And the second number is how much electric field can it withstand before it will cease to function in its proper manner. So we have something called dielectric strength. The dielectric strength is simply a number which is the upper limit of the external electric field that it can withstand before the thing snaps apart. Okay? So dielectric strength is simply the maximum E external that the material can withstand. And if you look on the third page, the data page, on the formula sheet, that's the miscellaneous page with physical constants, math, physics 1 stuff. You will note in the lower left-hand corner, there is a table, which will, this is not to be confused with the lower right-hand corner, which is resistivity information, which you probably already used on homework 5. The lower left-hand corner, there is a table, a data table on dielectrics. I just basically stole it from the CRC. You guys know the CRC? Okay, it's a book about this thick. Well, you guys probably get it online these days. It's, what does it stand for? Chemical reference something or other? This is like more chemistry than anything else. You guys don't use this in chemistry, CRC? What is it? Oh, yeah, just call it the CRC. It's basically a thick book where you can look up whatever you want for physical constants. It's mostly chemistry, but it has tables for coefficients of friction and resistivity and dielectric constants, stuff like that. Basically your catch-all for any physical constants for any material, if you want to know the material properties. it becomes your friend when you're an engineer and you're like, I wonder what wood properties have, or whatever is chemical, okay? So on that table, you will find a list of different materials. You'll find their kappa value, which is basically their booster or multiplier for the capacitance, right? And then you will also find next to it the maximum electric field that it can withstand before it gets torn apart. Because these two things are two sides of the same coin, right? Think about it like this. Your ability to separate out the plus and minus is what gives you the E induced in the first place, right? If a material wasn't very good at separating out, a given molecule wasn't very good at stretching the minus and the plus from each other, it would be a bad partial shielding. But anything that stretches also breaks eventually. So you have this balance where things that tend to be good at stretching and giving you a high kappa value, because they're really good partial shielders, also tend to break very easily, because what stretches also breaks. Right? The ideal material would stretch a lot and then not break, but that's not realistic. So when you're designing a circuit, you need to definitely know in your application what is the largest external electric field that the material could be subjected to. And you can work out what that is by knowing what voltage will be applied. And you then want to say, I know that the most charge I'm going to put on this capacitor, and therefore the largest external field that they can create is this, whatever number. And then you say, I'm going to go to my table and I'm going to scratch out all of the materials that would break down under that. And then the ones that are left probably want the largest kappa value of those, right? So that's the kind of considerations that you want to use. You want to use, if you want the largest capacitance possible, you also don't want it to break down while in use, okay? Usually, this is a bad feature, okay? Especially if you have a capacitor that has a solid material. If you tear it apart, it's never going to be the same again, okay? You have permanently altered the structure of it by tearing apart the molecules. Now, there is one example, I don't remember, I think it's next homework, where I give you a renewable material. In fact, the dielectric material, like air, is a gas. So you can actually use dielectric breakdown for a purpose. You can actually use it as a flash. So there's a problem where you have a blinking light on a construction site or something like that, where you're purposely using dielectric breakdown to create a little blink, okay? So that's on the next homework, I think, okay? So dielectric breakdown, generally considered a bad thing, especially if the dielectric material is non-renewable. Once you break it, it's broken. But there are other applications where you can replenish it, and then it's a feature and not a flaw, okay? For air, I'll tell you right now, air, the external electric field maximum, or dielectric strength, is around 3 times 10 to the 6th megavolts per meter. Oh, sorry, that should be volts meter because I already gave you the 10 to the 6th, so, or 3 megavolts per meter, okay? So if you were doing the homework over break and you felt like there was a missing piece of information, that may have been it, okay? So that's a number that appears several times on the homework. What I have you do is I give you a comparison between the dielectric breakdown of lightning, something like that, and on a much smaller scale, the mini lightning create when you scuff your feet across the carpet and you go to touch a doorknob, right? There's a little spark that jumps. And what I have you compute in both situations is what's going on. The voltage, or sorry, the electric field necessary for breakdown is the same in both cases, but as you will find, what will kill you is the transfer of charge, and the transfer of charge is much different. So lightning strike, that can kill you. Touching the doorknob after you've scuffed your feet across the carpet, it might be painful, but you don't have to worry about your demise when you're doing that either, okay? So same electric field, but as you will find, the charge transferred into or out of your body is very different. Okay. Okay. Are there any questions on that? Okay. So that's dielectric breakdown. Going along with every kappa value for every material, there is a dielectric strength, and those are in the table. So that right there is the end of your homework 6 material, and let's see how much of a jump start we can make on homework 7 material with the remaining time today. More on capacitors. So capacitors is a large enough topic that we split it off into 2 homeworks. This, by the way, what I'm just starting now is the subject of your RC circuits lab, which will be next week, so I'm definitely glad I did not schedule it for this week, because you would have barely seen the topic in the remaining 11 minutes today and Wednesday morning, and that would be a pain to do that lab Wednesday afternoon. So let's see what we can get done. This will be your next homework and lab next week. RC circuits. And so RC circuits, these are circuits that have both a resistor and a capacitor. So thus far, capacitor has been something we could connect it directly to a battery and just charge it up. Whereas now we're going to take all the circuit elements, resistors, capacitors, and eventually batteries, and put them into a circuit, and we'll see what happens. The biggest feature of these circuits is that for the first time, they will be time evolving, okay? So unlike our normal batch of batteries and resistors, when we connect them up and then we establish a current, that current basically continues forever. If we neglect that batteries eventually run out, there's a steady state current that forms and flows, and you don't have to worry about what's happening earlier versus later. But these capacitors allow there to be a time evolution of behavior in the circuit. So anytime you have any circuit whatsoever that does something over time differently, you can be willing to bet that a capacitor is involved in some way in its function. You will take whole courses on this, analog and digital circuits and all that stuff. We'll just touch the tip of the iceberg. That's what physics is. We just take a look at a bunch of bins and set you up for some later coursework where you get into those bins. So I want to start with the easiest circuit. This is what I'll call a standard discharge circuit. So I'll look at what's called a standard discharge first. I'll do a standard charging circuit, and then I'll look at just the tip of the iceberg, some non-standard circuits, and leave the rest of it for your circuits classes. So here's what we have. We have a capacitor. Now, it can't discharge if it doesn't have any charge to start with. So let's say we've charged it up in the past. It's got some charge. So it stored some charge, it stored some energy. I'll call the charge here, let's call it plus Q, minus Q. And let me set myself up here by discussing all the properties of this capacitor. So let's talk about charge, voltage, energy. Okay, that's a good list. That's pretty much it. So initially, I'll say that the charge on each plate is Q naught. So that's at some point in the past has been put on there, plus charge on one plate, negative on the other. This stores a certain amount of energy, and the voltage as well is at some initial value. So let's say I charge that cap up with a 9-volt battery, so the voltage across it is 9 volts. Okay. It actually doesn't matter if there's a dielectric in there or not. The dielectric, of course, would allow these values to be larger than they would have been otherwise, but whatever those values are, that's my starting point. Now I'm going to take the charge and energy off of it. I'm going to utilize this. So, I'm going to connect the plates. And I'm going to connect them through a resistor. So let's talk about what happens here. Well, before the capacitor was charged up but then became an isolated islands of charge, there's nowhere for the charge to go or come from, but now there is. So these plus charges don't want to hang out near each other. They're going to flow, go through the resistor, and once a plus charge flows, it's going to cancel off the minus charge. Now, again, if you're weirded out by the fact that the plus charge is moving and the minus charge stays stationary, I can remind you that it's all really the reverse, right? Really, the minus charges are mobile. They go up toward the top plate, which is positively charged. And that is Ben Franklin's weirdness that's with us today. Of course, all the conventions are backwards. So we take the current as the hypothetical flow of positive charge to lower voltage. So other things we could ask about. What's up with the current? What's up with the power? Because of course, as charge courses through a resistor, there's going to be some energy dissipated. Like so. So there will be some initial current, which I'll call I naught. Why am I calling them not? I think in my notes they're called initial. I like initial better, sorry. I like initial better. I hate not. I don't know why.
I hate it too.
Okay, so that's the initial current that flows. Now, the current's not going to flow forever, right? Because at some point we're going to run out of charge. Eventually what we're going to have is that all the positive here will join up with all the negative here, and then we have two neutral plates, right? So what does the charge go to eventually? What is it? Zero, that's right. So then the current's going to stop flowing because there's no more stuff to flow. What's going to be the voltage difference across the plates when they both become neutral?
Zero.
Zero, that's right. And how much energy is stored on the plates?
Zero.
Zero. Everything's running down to zero.
Because we discharge them.
By the way, where did the energy go that was stored on the capacitor?
Through the resistor to
It
heat.
got sweated out, that's right, to the environment, through the resistor. And in fact, the initial rate of which is, of course, determined by the current, right? So we know P equals I squared R.
Yes, sir.
So if the current runs down to zero, eventually the resistor stops sweating out heat because there's nothing left to sweat out. So everything just runs right down to zero, okay? So you might ask, well, okay, if everything goes to zero eventually, how does it do that? Does it just do it linearly? Well, that would be nice, wouldn't it? We like linear functions. But it's not linear, and the reason why, as you can imagine, these plus charges, when this plate is relatively full, the plus charges violently want to repel each other. Or another way to think of it is that there's a large voltage difference, so there's a lot of motivation for the charges to flow. So they're very excited to flow at first, but later on, when it's almost empty, right, it's not that exciting. So there's only a very few positive charges left, the stragglers. They're not going to repel each other that violently, and the voltage difference between the plates has become pretty minimal. So it's a it's pretty annoying to have to go through a resistor to get to barely lower voltage than where you left, right? So what we actually find is that the rate of the flow is proportional to the amount of charge that is still on the plates. So we'll find a high rate of flow when there's a high amount of charge left on the plates, and we'll find that the rate of flow is very small when the amount of charge left is very small, okay? So the rate of flow is of course called the current, which is dq over dt. That's the rate of change of the charge, and the amount of charge is of course q. So we find that the rate that charge flows is proportional to how much is still left to flow. Now, this type of relationship occurs in nature so much, not even just physics, anywhere in any science, and it should immediately trigger you to think one word, and that word is exponential, okay?
Yes, sir.
Anytime, anything where the rate of something depends on the amount itself, that works out mathematically to an exponential. So we will next lecture look at how all of these guys decrease towards zero and do that exponentially. And we'll work out the exponential equation.